in this institute with many MTech and PhD students. Under his supervision, many of the students already have completed their PG and PhD degrees. Today he will be talking on natural hazards and seismology. So over to Dr. Arjun Sil.
Thank you, Amit. Uh, and good morning to all of you. First of all, am I audible to everyone?
Yes, sir. You are audible and you are visible as well.
Okay. Okay. So good morning to all of you. So hope everyone is safe and fine in your home in these difficult times. So, and I would like to it is a pleasure that the organizing committee consisting of Dr. Amit Kumar Das, Dr. Atunu Shahu and Dr. V.K. Roy invited me for this lecture in this workshop. So I also welcome to all participants. I will be shortly now going to this presentation which I will be delivering today. So I hope now my topic is actually seismic hazard, mainly the seismic hazard assessment, seismic hazard assessment principles, and like your arcuation design. Okay, so I will mainly discuss this topic especially related to the seismic hazard and like how this what is hazard and how this seismic hazard is actually affecting the infrastructure or our built up environment. And what are the mitigation strategies like in terms of say arcuation design and its concept. I'll try to brief in this presentation, but emphasis will be seismic hazard along with the other associated hazards. So before I start with this discussion, specifying the seismic hazard, first we have to understand what is hazard actually. So many of you might have known. So like first hazard, what does it mean actually? So this hazard actually like your so various types of events are actually associated with these like it can generate hazards. So first if we see like what we are experiencing inside the earth, these are actually like our inside of the earth and outside, like inside world and outside world. We can divide it into two terms. So outside world, suppose if I talk about, so if we see just think about the galaxy or our universe, this is actually like also we use this term as a dynamics. This term, like our universe is completely dynamics condition. Otherwise, this kind of activities, and what kind of activities we are talking about here in terms of say hazard, of course, but what are the activities actually is occurring outside world as well as the inside world, but especially here, like say outside world, you will find, although we know till date that except the Earth, which is a planet, one of the planet like in the solar system, having a life, existence of life. But apart from that, till it is in searching mode, like there is no any life living particle even like these are under investigation. So this is our curiosity that we are looking for in the outer world. So now, if we think and think about the universe, what are the contents, specially, or what are the controlling forces, or actually is responsible to maintain this kind of dynamic activities? So then this comes in our mind, like one is, say, simply like three things, three phases or stages we can think of in various forms. Spiritually also we can think of in scientifically also, and we can, of course, we can connect it some of the cases like scientifically as well as spiritually also. So here, especially like if we think of the whole universe in general sense, actually these are actually, if you find, you will see that only frequency and the energy uh, exist for the universe. None other than this actually you will find. So like this process, like again we know that energy is a like a dependency of the frequency contents, if we think about. So like this and if you see that how this wonder or the surprise that has controlling this whole universe, just like all the planets, heavy massive planets, are actually moving and they are following some basic principles, and these are periodic. You know, if you think see or even realize. So so that means some in a discipline like in a discipline like a mode, these are actually performing their functions. Now like this energy, what are those energy? Three phases of energy. One is a creation, like creating energy. Another is destructive energy. Another is in between, that is a transformation or transforming energy. So these three phases actually are playing the major role in this whole like this dynamic process. So now whatever is happening inside the sorry, outside the world, like outside world or the universe, like in terms of hazard, if you think of like say space debris, okay, space debris that can also affect on the planet, as well as space debris sometimes it may be artificially also, it can be, and this can create a hazard. Hazard means damaging potential or risk involved in it, which are going to be exposed due to these events. So in this case, actually we are actually looking for, say, space debris, like some satellites, like so many satellites, more than say more than 200 or like not 200, sorry, it is about to 3,000 now, as of now, in and around the earth. So many material, like when after like functioning of these satellites also, you will see so many debris materials. These are floating outside that earth or within the space. So even some asteroids, like naturally, so many asteroids, including like say meteorite. So these are actually even has a threat or like a hazards, creating hazards in like inside of this earth, or even like these are the process. Like it is not like that it is happening just one time or like that, rarely, but it is happening frequently. But some of the cases which is coming closer to the earth because of this gravitational attraction of the earth, so these hazards may be experienced by the interior of the see inside of the earth. So so simply we are looking for the, say, risk. If we talk about the mitigation strategy, and also finally we are looking for the risk, actually how much risk is involved for such kind of unwanted incidents, and which is occurring naturally or artificially also. So this is a space related hazard, like I would say this is a space hazard, that may affect to the inside of the earth surface. So now you may think of what is risk even. So if you think of that as a like risk is actually specially defined by hazard into vulnerability into exposure. Okay, if we think of in that sense. So hazard, say there is a damaging potential will be always there. Suppose for say right now what we are facing is a COVID-19 pandemic. So now this is also one of the risk involved associated with the current scenario, that is on human, like a human to human transmitted disease. So like disease, so this actually it can affect also in the risk like association. So like your body is say having, not every human body is having a like more or less some say facing some health issues, like which we call it some disease, suppose. So this is a normal, under normal circumstances happening due to various reasons, various factors. Similarly, like now this is a, so our bodies actually say hazard is automatically say germs and bacteria are in and around with us. So this is just like your body is actually now hazard is actually there. Now your body is now you can control your body by boosting your immunity, like so it, even by deteriorating the immunity, so it can affect you. So this is just like a vulnerable, your body is a vulnerable as like a component. So now exposure is now COVID, say this virus, COVID-19 is also is adding additional like exposure. It is a exposure. So and finally, if you add this exposure, so automatically your risk is increased. So like that. So for the same person, if you think like one person is sitting over say India, in India, or is some other say one place, and same person having say risk, say in a hot or say I'll say areas, and some same person is moved to the colder region or areas. So automatically this exposure is actually will be enhanced in case of cold, suppose, so as of now we know. So it is a even region to region. So you finally what you are actually risking yourself more when you coming closer to the like this kind of exposure, whereas same person may be less risky in some say warmer areas even. So like that. So this is how the actually exposure is actually triggering the risk. So now hazard is remains same for that kind of particular person, and because virus normal diseases everywhere, suppose you will be experiencing more or less. So this is something. So only that new virus is adding a additional risk, which is finally resulting you are facing a higher risk. So like that. So every system actually facing this risk because of some hazards, and these hazards are actually generated due to the mainly destruction, like destructive energy. Like, so like, and throughout universe, like throughout the universe, we can even think of like we can compare it to the our like even atom also. Like we can see this basic principle is actually also is being followed in a atom, in a like a atomic configuration. You see proton, electron, and neutron. So so these are also following, these are following some path or orbits, like called outer shell, like where electrons are moving and proton and neutron is at the center. So that's why we are experiencing heavy mass at the center. Also, like in engineering, that's why we CG, center of gravity, already we are calculating while calculating forces also. So these are actually connected. Basic physics or fundamental part is actually the same, remains same if you think, but your exposure, your events may be coming in different way, but the basic process is remains same. So similarly, in outside of the world, so this kind of say hazard actually is experiencing. Now you can say like how much like risk is involved associated with the outer side world, like asteroid or meteorite. So in that case, it is according to the research, it is found that around it is normally not affecting to the Earth environment, but it is a rare say something like that. But if it when it will be more risky when it comes to the actually that is called Leo. Say we know that there are three altitudes in which we are actually installing our various satellites. Like one is called Leo, Meo, and Geo. So when the this kind of debris comes closer to the Leo means lower Earth orbit, medium Earth orbit, and geostationary Earth orbit. So geostationary orbit, like all weather satellites will be like moving like this is moving at that particular height, which is a higher altitude. Medium or say orbit, or that orbit is actually at the middle layer, medium height. So low Earth orbit is actually close to like your mobile and other TVs, like all kinds of signals which you are receiving. That is because of Leo, those satellites which are moving on the Earth, and it is installed there. So like that distance or from the space, when a meteorite or asteroid is coming closer, so it is around, its speed is around 7 times like higher than the bullet speed. So in that case, you will see this is going to hit that particular area inside the Earth. So then this will be creating a tsunami. Also, you can see, or even this destroy that particular city or the area or the region. So this is how actually this space hazard actually is contributing this disaster inside the Earth also. So now, like coming to these hazards, like what are the types of hazards? Like say it is can be man-made, or it can be naturally generated or created. Now, these natural hazards, already you can see earthquake. Okay, earthquake, even flood hazard. Due to flood also we can see, or we are experiencing various types of flood hazard, like due to flooding, so many destructions seasonally we can observe. We used to observe even in our this Assam, especially like every year. So this is also a very like a destructive in nature in a plain areas. Okay, so due to flooding. So now say wind. So wind hazard. So wind is also somewhere some places winds are actually speed is very high, and you know that more or likely the like tall structures are actually getting affected due to this wind hazard, and this can create a disaster. Similarly, droughts, like due to high temperature, humidity where will be less. So in that case also we will see this kind of drought hazard, like dying of living like plants, animals, whatever, and the area also it is an created, degenerates unfertile land also sometimes. So and finally, like typhoons, cyclones, so those kind of also are responsible hazards on the earth surface, even blast. So blast may happen. So this is of course a man-made as a blast can happen. Say aggressive environmental hazards, like you can see all kinds of materials which we are using they on daily basis. So these are actually some deterioration is happening. There is corrosion also you can talk about. So this is also due to the aggressive environmental hazards that can be considered. So which is deteriorating the metal mainly. So metal surfaces. So now space hazards already now we have discussed, and radiation hazards. Another is radiation hazards, like whatever say mobile tower, say even say nuclear reactor or the nuclear radiations. So it may especially say telephonic tower, even you can see so many problems we can observe naturally also that there is a changes. So these kind of hazards actually creating a health hazard actually finally. So all are actually coming under hazard. Now man-made hazard, again say nuclear, due to nuclear activities. So nuclear blast also like is responsible for generating a nuclear hazard, and mining also is responsible for say landslide and all, say sometimes, or even say immediately collapses the nearby this environment also. So like that, and life losses can happen also. So so mining and quarry blast, so these are human induced, and collision, you can see traffic hazards, they means especially the accidents that are taking place unknowingly also. So these are actually coming under hazards, traffic hazards, human induced hazards. So and then mitigation strategy may help in this to cope up with these kinds of or to neutralize such kind of hazards with adopting the appropriate scientific strategies. So these are all hazards actually. Now question is, among all kinds of hazards, why earthquake hazard is so important actually? Why we are considering this earthquake is a very important, one of the important hazards among all the hazards especially. So reason is actually, if you see like even radiation hazards also is responsible, but it is a human health, creating a human health hazard. So and it is happening slowly. Time is taking even more than say 10 years, 20 years, say decades at least to identify that because of this radiation the health that has been deteriorated. But in case of earthquake hazard, just the opposite. Like both are actually widespread destructive in nature. But in case of earthquake, opposite the characteristic is actually earthquake is in a very moment, in a very fraction of second, millisecond, earthquake can destroy the huge area, like larger area it can affect. So that is the basic difference you can think about. That's why radiation hazards like we are experiencing in a very later stage. But in case of earthquake hazards, we are facing instantly, even before we perceive, before we get into know about it. So it is happening, and it is very uncertain in nature. So it suddenly happens. You can say in that direction. But how it is creating a high destructive in nature? Because if you see that actually all kinds of due to the all the structures, if you think about in terms of your mechanics point of view, hazard is mainly generating the some forces finally when it is experienced by that kind of particular structure, maybe building, maybe bridge, maybe tower, it can be anything. So when it is affected, that particular structure, so finally it is actually destroyed, that is called shear stress. Actually it is generated due to that kind of seismic events. And you know that any material is very weak or behaving just as a weakest nature when it is encountered by shear stress when its shear strength is like exceeding. So in that case, most of the structure, when it is earthquake hazard is actually impacting on that particular structure, so automatically the structure loses its shear strength because it is exceeding at that point. So it structure all the most of the structure, whether it is a structure non-structural or structural members, so it is automatically collapses. So that is the reason like that why earthquake hazard is so important and how it is affecting. Now, if you think about this contribution, like according to the Indian scenario, if we see, so say India is experiencing by this earthquake hazard, landslide, as well as flood, cyclone, and droughts. Among them, it is estimated that around 60% of area is highly vulnerable for due to the seismic hazard. And landslide, you can see that is around 15%. Flood, it is almost around 12%. Cyclone, it is 8%, and drought, it is 6.8%. So these are the the contribution in the India. So that's why earthquake has a very major role in our infrastructural activities, or to make in terms of mitigation, or like a capacity building point of view. So that we have to give more like extra attention or more attention compared to the other hazards. Of course, some of the areas like Assam, flood is also very important, like playing a very important role in disaster. So we have to, that is also our one of the major concern. So like that is the regions specific like effect or the hazard that is experiencing every year frequently. So that all this we have to now find out the solution, or mitigating like steps need to be find out. So these are the Indian, according to Indian context. So now say base shear. Now, as we are talking about the structural, like how this earthquake resistant design concept is being evolved or coming in picture. Actually, you know, as just now I discussed, like how this structure is actually like experiencing by this force which is coming from the earthquake, like that is called seismic hazard which is associated with the earthquake is called seismic hazard. Now seismic hazard, as I said, earthquake is a very important role. So it is like base shear. We are first calculating the base shear, and it is just acting as a cantilever and for in the structure, and finally these are acting as a lateral force. And finally this is actually another thing is like structure should be like like its load distribution should be uniform, so that it does not create additional moments. That is also another of the important part while in designing. That's why your structure should be like simple, at least in terms of configuration, so that additional moment, bending moment should not be generated due to this your irregularity, vertical irregularity. So that should be taken care of. And this force is finally affecting throughout the structure. Now another important thing is, again, structure should not be massive also, because more massive structure you construct, it will attract more force, because mass, I mean, if you see that equation of motion, so you will see that force is actually if there will be heavy mass, it will attract more force. So our structure should be also that lighter, in that accuracy design concept. So lighter material may help to reduce the mass, which will reduce the attraction of lesser amount of forces. So and it will not create that instability, lateral instability. So all this, considering all these aspects, so we have to design even like these various kinds of structure, like low rise, medium rise, and high rise structures, even in various geometrical structures in planar form, also may contribute your increasing or enhancing or even reversing in nature, like you're increasing or decreasing the, you can control it mainly. That is what the, which is a mitigation or the controlling strategy, how to cope up with that kind of seismic forces. So you have to like find out. So for small low rise structures, it is acceleration sensitive, we know, and medium rise it is a velocity sensitive, and high rise structures it is a displacement sensitive. So like this you have to find out actually, so you find out the solution, and you have to solve your problem in such a manner that structural capacity should be always in higher side compared to your load exposure. Now you can ask, or you can think about that how the load is distributed, like finally in the design process or analysis and design of a, say, structural analysis or structural design for this kind of lateral loads. So what it does, additional, say, loads which is generated, or even in dead load or live load also, when you design a structure, especially considering the various exposure condition, like say dead load, live load, earthquake load. In that case, earthquake load, like or even dead load, whatever load is coming, we are designing each and every member, like every member, every component of the member, like acting as a individual element, and whatever force is being experienced by that kind of member, it is actually how it is transferring. It is transferring through moments from one point to another point. So like this, we know that energy also cannot be destroyed or created. So similarly, whatever force it is experiencing, so there should be some displacement. Like that's why we go for, say, we always try to find out, see, that is called indeterminacy, static indeterminacy, kinematic indeterminacy. So in that case, like finally what we are looking for, we are looking for the finally work done, like force is, say, SI in each. After analysis we are getting at each and every nodes like SI and KI only. Like these are actually static indeterminacy and kinematic indeterminacy. So static indeterminacy is unknown forces which is like induced at that particular that is expected force after analysis what you are getting. So that is you are finding out, and from that force, your unknown force you are finding out, as well as the displacement in terms of rotation, deflection, say like that. You are like linear or angular rotation you are finding out. So whatever you are getting there in terms of displacement, so these are actually finally coming to the work done. So you finally, if you work done is done through like how, when it is transferring the loads from one point to another point, say from slab to column or beam, suppose. So it is transferring the load how, through this force into, say, distance mode. So and this finally you are targeting to the work done. Work done is nothing but the energy. So like that, this whole process is continuing throughout these components, individual components, like say from part to whole, finally global, like a global response we are finding out, considering the worst scenario of the load combinations which we are achieving from this, say, earthquake, a combination of dead load, live load, and earthquake load. So finally it is designing, you are designing your structure considering the worst combination, and finally coming out the worst responses. So in that way, finally you are actually designing your each and every, like you are finding out the very worst component of the member, and then you are actually designing accordingly that kind of member, and finally giving a proper design, like its dimension, its reinforcement, so also and so on. You are actually providing and giving, following the ductile detailing, and as per the codal standard also you are following, whether it is exceeding or not. So this is nothing but the capacities. You are ensuring each and every point that your structural member, globally as well as locally, should be adequate enough, its safety, its stability, safety and serviceability condition. So this is actually we are following in the like design, like aspiration design or whatever, even other cases of design also. So this is so that's why this analysis and design is actually very important, and also like all these load transfer process we have to understand to give the structure in a to perform the better like output in that safety directions. So now this is a now suppose this is the seismic hazard throughout the country. They expert committee has recommended this map in terms of zonation form. If we see that whole country is divided into zone 2, 3, 4, 5. So these zones we are familiar with the design, like zone 2 is the lowest experience hazard, like 0.1 G, and maximum is 0.36 G. Others are say 2.24 and 0.16 G. So these are actually classified, and highest if you see our northeast, northeast as well as you see the northern part of the India, including say Delhi, Jammu Kashmir, Srinagar, like, and Bhuj also. So these are actually coming under zone 5, which is a severe zone or highly seismically active region in the world. And we know that northeast is the 6th most active tectonic region, BAL, in the world, because if you see this say from east to west direction, it is actually a tectonic collision. If you see that in the north to south direction along the Burmese, so it is actually subduction. So and inter and intraplate activities are also actually involved within this plate itself. So and makes this area highly complex seismotectonically. It makes a complex shape. So that's why it is very high hazard throughout the country, and we can see also every time we can see so many earthquakes are actually generating. So this is the so the and problem is this this donation actually what is the main strategies actually in this map. As a map directly we are taking this value and designing the structure, but finally we are this is acceleration only, say we can have it, but in the code it is given a design response spectrum, which is your very important. And for that, some cases like for highly seismically active areas, you have to do microdonation studies for in terms of site specific study, which is not say not like in general or say medium hazard that can be experienced. For that, this code is enough at least to adopt. But for microdonation study, say for very highly seismically active areas like zone 5, you have to deal with very important structure when you are planning to construct. So microdonation process you have to adopt, which will identify the like seismic sources, that is a fault or the structure point or the fracture junction accurately through spatial mapping and assessing say the hazard in a very site specific manner. Then only you will be able to find out for that particular structure how much force a future say generating earthquake can induce, how much forces that, so that this structure can be easily absorb this force with ease, or having the structural capacity should be higher than this expected force. So then only this structure will be stable. So for that you have to go for microdonation, because there is a again a site that is called site effects due to this soft soil deposits. Even in topographical variations or topographical say elevation, altitudes, these are actually responsible also like amplifying de-amplifying the like hazards. So that's why microdonation is an integrated part of this particular area. So you have to take care for that when you are planning to construct a very important structure. So microdonation is mandatory in that case. So now in the output form, if you think about the output, so this is what we are looking for, a particular say area in terms of microresonation point of view. Also we are looking for such kind of spectra, that is called a design and response spectra. Design response spectra is a function of say period dependent force, like acceleration or spectral acceleration. This is a spectral acceleration. So this force, it will be affected, and every structure is actually having its own natural period. So if you know this period, you can easily find out the say like a spectral acceleration, or even simply as acceleration, or even whatever, even spectral velocity, spectral displacement also you can generate from with respect to, that is called ADRS format. So you can generate it if you know the any like even say the spectral response, say this so from that you can convert it also the velocity or acceleration. So so this is a very key inputs in articulation design for any structure to design with a high reliability. So now, as we have discussed the importance and all, so now earthquake, if we talk about what is earthquake actually, so if you see, it is nothing but the shaking on the ground surface, like caused by a sudden release of energy actually on the earth crust. And earth crust is actually like floating on the, we know that earth crust is floating on the on the upper crust layer. Below there is a mantle actually. So it is under semi-liquid condition. If you go into below deeper case, so here so it is generating suppose say this kind of seismic waves. Okay, so seismic waves actually, these are actually nothing but the energy which is transformed in terms of waveform, which is the earthquake which is generated at that particular area. Now suppose if we see first, let us go to the internal structure of the earth. If you see here how earth is being formed, like this is the crust layer actually, which is actually if you see at the top where we are living on the earth crust, and and at the below there is a mantle. Of course crust is there, upper and lower crust, it varies spatially location to location, but so this is and below this you will see there is a mantle which is a semi molten state, and like behaving semi liquid form, having a fluid properties as well as solid properties kind of. So it is exerting, and below say exerting say continuous like pressure on the earth crust, and earth crust is actually that actually due to that shear, and some shear stress is generated due to this movement of this liquid inside the earth crust. This resulting interaction is creating a shear stress, and that stress is actually helping to move the plates slowly. So that is what plates are actually under motion or dynamics, and earthquakes are actually now due to the interaction they are occurring. Now if you see the below inside of this are crust, mantle and core, outer and inner core. So mantle is also upper and lower mantle, and crust is also upper and lower crust. So this classification, if you see, so finally this energy which is released at the source, so that is being propagated through waveform, which we have seen in this like your earlier in the like motion like form in the figure, that these waves are actually like body wave and surface waves. So P and S waves, and surface waves is R and L waves. So these body waves is like we know that these are moving through the body crust layers, and P is the highest speed, and S is the lower in speed compared to the P wave, and R wave is the surface waves, Rayleigh and Love waves. So these are long waves like characteristics because of the far larger distance, these are predominant. So these are actually affecting the whole earth layers or the environment, like our built up structures, and our structure is actually getting affected, and what we have discussed in the accuracy design, so that finally the environment is affected and structure becomes vulnerable and collapses also, we can see, because of our poor design or construction, mainly because we know earth, this is a natural process, we cannot prevent it, but mitigation is the only the steps or the measure that by which we can easily like estimate or find out our right solution, like in terms of mitigation. So this is actually like you have to take care. Now suppose so this is actually like some of the like details are given here, and this process, like the energy, how it is, this mental process is taking place inside the earth. Say some bands are actually moving, say, downward, is called subduction, and it is like a destruction part, like it is destroying the plate by subducting, and another is creating the plates, and another is say in between the movement is taking place, and the huge amount of earthquakes are actually generating due to this called transform fault, transform boundaries or transform faults. So and subduction boundaries or subduction faults. So you can name it in various forms. So when the earthquakes are occurring in a very belt or the plate boundaries, so these are called, say, these are like transform boundaries, like your subduction boundaries. Like that. So you can talk about, and so three forms you can find out for this, like this is energy, like how energy is actually like attenuating from even one place to another place, how the energy is attenuating, so that you can easily actually understand, and yeah, you can evaluate it in a phase manner. So also we can divide it into that's why, like, source, path, and site effects. So this is very important in the seismic hazard evaluation. Now if you see this whole like this earth crust, so these are actually all the earthquakes are occurring, that's why at the plates, as we have discussed, that because of this shear stress generated inside the plate, so this like energy is releasing throughout this belt or the fracture. So this is the, we can say that this is the weakest part of the earth crust, where these earthquake are actually generating. So, and this is how these fracture belts or the joints are actually being delineated, especially considering as a fracture or plate boundaries. So this is actually called even the movement of the plates and the interaction between the one plate to another plate. This phenomenon is known as like a plate tectonics also. So now if we see the basic process, like how the deformation actually is taking place, so you can say like you can say deformation, how this, there are three phases of deformation before just exploring, like explosion is taking place, like your say here three phases have been shown here. Like one is plate, one plate and another plate movement is actually here, it is taking place. There is no, it is under, say, equilibrium. So and suppose now fracture is taking place slowly, so automatically in the second phase plate tends to bend, and the automatically it is bending. You can think of the beam bending theory kind of. So, and similarly in the third stage, this is actually broken up into pieces and get separated from each other. So these three process actually is it is found that based on the seismology, seismologists, they have characterized it in terms of mathematical, they try to model this phenomenon. So they have modeled it in terms of function that is called Poisson's distribution. This whole process is actually, which is giving you the number of events that has occurred you considering these three phases for a particular cycle of energy breaking. So now how many number of events can be generated? So you can, if you know this, it's say mean value, mean u, and its number of occurrences is x, and so you can find out the number of, say like how many times this can, like how many number of earthquakes or how many number of times it can occur, that you can easily like find out using this concept, which is satisfying this fracture process. So now so how this process is actually, if we think about this figure form, like this Poisson's distribution, three types of events are continuously generating before fracturing of the plates. One is actually before, that is called, one is called foreshocks, which is actually occurring before the main event. Main event means when the like this plate is going to fracture completely. Just at that moment, it creates, releases a huge energy, which is actually shown in this figure. Suppose at the top red arrow line. So and then before all kinds of events which have been generated, these are called foreshocks, just to trigger the main event. And this is a fracturing phenomenon for which this small energy has been released before to trigger the major one. So so it is a foreshocks. And thereafter, if we see that when there will be a major earthquake, suppose, or we have already experienced when there is a major earthquake occurred, there some after that main event, so many events are also occurring compared to smaller than the main event. These are called foreshocks, sorry, aftershocks. And these aftershocks may continue even months, even say month, more than month, like 1 month, 2 months, 3 months also it can continue. So until and unless it reaches again in this equilibrium state, means at the equilibrium state, you can think of logically that your plate has been fractured completely, or disintegrated, or delinked, or decoupled from one another. So so this process actually continues one by one, and the plates are getting like fracture is continuously taking place and earthquakes are occurring. So this is a basic phenomenon. Now say how many earthquakes happens on the earth crust, and it is one of the way to release the energy actually, because you know that these are nothing but the earth follows various energy cycles. So these energy cycles, it is due to maintain its dynamic state, it has to release this excessive amount of energy, which is imbalancing its natural processes. So that energy actually is released through this earth crust or the fracture plate boundaries, and this is how it is balancing its energy balancing ecosystem inside the earth process. So and if we see this year wise, this how much energy has been released in terms of earthquake energy. So at least one earthquake more than magnitude 8 is occurring like on an average basis every year. And then say if you think about say 2-3 earthquakes are occurring 7 greater than 7 and above. And similarly if you go back to the lower magnitude, it can go even how many, it can be more millions, like more millions of earthquakes. So it is making a like a gradient, slow, like a slope line, like frequency, earthquake frequency occurrences. So so now this is actually just like if you I have to taken say 2 days say even for say 2 weeks data. So if we see that, say automatically most of the cases you will find all the earthquakes are occurring along the pals continuously. So it is understood that all the amount of energy which is released, it is through the through the plate boundary, or the like where the fracture is where the stiffness is very less, or crust is very having a lower in capacity in terms of strength. So energy has been released in that area. But you can say that after this continuous fracturing process, say no area is safe. You can say in future that earthquake will not occur in that area. Now the area which is silent even, that is called, of course, say you cannot say that in that area earthquake may not occur in future. So continuously this is the process, and earth may changes. It's like an energy cycling process, and it can reoccur in some other locations for releasing of this kind of energy. So you don't we it is very highly uncertain to like identify where the energy is going to be released. But most of the cases, like we see, putting the seismograph actually in various spatial locations, we can easily identify various locations where the energy has been released through the earth crust. So, and we can map the plate boundary in a revising of the boundaries. We can do it, and that's why even code also we can see like earthquake codal provision we are changing after say decades wise. We are revising these standards also based on the seismotectonic setting of the region. So but it globally also we can change it once a global study can be done simultaneously, and we can come out with a revised map. So so it will be changing. So this is some of the earthquakes which has say occurred in the northeast India so far, more than magnitude 7 and above typically. So now and say these are the steps that we can follow like for seismic hazard as well as the micronization. So what I have to do is first one is your seismic hazard analysis using say deterministic and say probabilistic seismic hazard assessment, and for that input will be geological data, seismological data, say, remote sensing data also, and region specific attenuation model that is coming from the like path effects. Okay, path effects, source path and site effects. So path effects that will give you the attenuation characteristics to quantify how the energy in terms of wave will be will be impacting in some special locations. So that you can easily measure. Now outputs are possible outputs, like you have to say magnitude, how much magnitude that particular area can be experienced as a for a particular area. It may experience say magnitude more than 8 in the next year, suppose if we talk about by forecasting. So for that kind of particular fault, we can estimate the maximum probable earthquake that may generate the or that may trigger the seismic hazard for that area. So that you have to find out then what are the controlling sources that are responsible for generating the seismic hazard. That also we have to identify through our by identifying the faults or the fracture locations. Now now seismicity parameters also we have to find out, like from the data, earthquake data or catalog collected from various seismological agencies. Now output will be another is hazard curve, uniform hazard response spectra, peak ground acceleration and spectral acceleration. Similarly, now this is as it is if you want to do microzones, then you have to go for site characterization, that is for say for site effects. So geology, that is a geotechnical part. So so you have to find out through various geotechnical testing and get the site response study and come out with the surface level hazard, you can say. Then cytosol liquefaction also you can do it, and finally you have to integrate in a micronization whatever hazards are actually associated with that area. So this is a typical locations like seismicity in the study region. Say here I have shown here is a northeast, that is a Assam, which is a 33 districts. So like this like first of all study area, like what are the sources, like we have to do, what are the methods even we can adopt it is for this area is like deterministic seismic hazard and probabilistic seismic hazard. Any method we can adopt it, that is a standard process we can adopt. Now deterministic, there are some advantage and disadvantage of using both the methods, but most of the cases in a very robust study we use both the methods simultaneously and calculate or estimate or map that particular expected like hazard in terms of acceleration, velocity, or displacement to like to propose for that area that this is the seismic hazard, expected seismic hazard of the area or the region. So deterministic seismic hazard is very simple and straightforward. Like it takes the distance and magnitude and find out, you have to find out like its magnitude, like probable magnitude. There are some stats I will show, and another is the events or the earthquake data. So whatever earthquake data like like you will be having, so that should be processed. That is called declustering process. So you have to do it, and then this, after this declustering is like separating the like various cluster data, like foreshocks, aftershocks. From that you have to extract the main event, what we have just now discussed in the process physics fundamental understanding. So that is a declustering process, and then from that you have to extract the main events. Once you extract the main events for a particular fault or band, so seismic source. So then next is your say, once you declustered and then identify the main events, then you estimate the seismicity parameters of that particular area using like frequency magnitude, that is called equation or the relation, the Gutenberg-Richter relation. So from that you can easily find out. And in this DSHA, like it is considering this very nearest distance or close distance between the source and site where it is located and the area of interest. So, and that you are finding out the seismic hazard that is possible for that area. And you are another is you are actually calculating this through attenuation model, that is called attenuation equation or ground motion prediction equation. So that equation is developed in region specific manner. So you cannot use some of the equation which is proposed for say USA, you cannot use it for the Indian region, but you can use it only after verifying or investigating the similar characteristics, seismicity characteristics, like its fault characteristics is same, it's like generating the events is also same, whether it is a subduction events, whether it is a plate boundary active events, or it is a intra or inter events. So simply considering the seismotectonic characteristics, if it is matching, so you can adopt it. Otherwise you have to take your own data, that is a through data acquisition system, like by installing seismographs, those reliable data which are occurring day by day or time to time in that particular area for a longer duration of time, say more than say decades, more than decades, is it can be 100 years, even it can be 50 years, 100 years, 200 years, as if it is larger in duration, so it will give you the good or the realistic behavior. Also another problem is like earthquake is a rare event, mostly the major events. So so because of that, you will not get the data like immediately for all the areas, even for active areas or seismically active areas also. So in that case, it may be silent also, that is called aseismic or seismic gap. So but in that case, it is just, you can think of that it is gaining the or accumulating the energy through this because of this high aspirative characteristics. Aspirative characteristics. So that is called like it's very strongest point where it is absorbing or taking that amount of energy continuously without releasing. So in that case, once it is released, when it exceeds that particular kind of capacity, so it may like explore this energy. So in that case, it may generate a higher events, even more than 8 earthquakes, which are occurring. So with that kind of events, it can generate. So as Earth medium is a heterogeneous, so it is very complex actually, like to generalize, and even forecasting is also very difficult in place to place or special in nature. So so we go for a site specific study to estimate the seismic hazard. And probabilistic seismic hazard is actually like the difference is it is similar to the DSHA, but difference is here like it does not consider say closest distance or nearest distance. It considers the whole like the seismic source length along the length, and it takes each and every incremental incremental fragment or say segment of the fault component as a small seismic source, and probability is considered equally likely. So say magnitude as well as magnitude also as well as distance also in that case. So these two parameters actually is dependent with that kind of like attenuation equation, and it is uncertainty is being considered here, like your uncertainty in terms of probabilistic terms like standard deviation or standard error. This is being considered here to like while calculating the PS probabilistic seismic hazard or PSH at the site of interest. So so this is a important part. Now objective in the seismic hazard assessment is first understanding. You have to understand and identify the seismic sources in the study region, considering the current scenario, whatever earthquake has occurred in this area till date. Before studying, you have to accumulate or collect or extract all this information and gather the all available information till date, and then plan for further assessment. So in that case, this is a identification. Next is your collection of earthquake events. Like earthquake events means earthquake, whatever event has occurred, like magnitude in terms of magnitude wise, in a decade form, long decades, and make a database systematically, putting a from say like its second, minute, at what time it has occurred, where it has occurred, what was the duration. So all this information you have to collect and understand or perceive it, and then after collecting this, next is your active fault or potential fault or controlling fault. Like those in active faults means within the active fault there may be a controlling fault or controlling sources, seismic sources. So even say if you have active faults, all active faults may not generate the earthquake. So among them, say one or two may generate the earthquake, or one or two may affect severely in your area of interest where you are trying to assess the seismic hazard. So in that case, controlling source is very important among the active faults. So all are important. You have to find out the what's combination finally. So and then you have to find out the seismicity parameters and their maximum probable magnitude or earthquake in each fault, and then ground motion you have to select. As I said already, ground motion equation GMP or the attenuation model you have to choose in such a manner, or you have to propose by analyzing the detailed database like ground motion history, like what ground motion data has been recorded. So those data you have to from those data you have to estimate the you can propose the ground motion empirical ground motion prediction equation. and you can use it for reliable estimation of the ground motion for this area. So now a seismic hazard curve, which will give you the probability of accidents, mean annual rate of accidents versus the for a particular like probability in a particular site. Say for PGA, PGA is mean annual rate accidents is 2 and above. This is the say occurrence. So like a frequency of occurrence. So like that, a seismic hazard curve will give you the like 2% probability of accidents or 10% probability of accidents, so that you can easily estimate from the seismic hazard curves. So uniform hazard curve also you can estimate from that, which will be further can be converted into a response spectrum, okay, or design response spectrum. You can convert it, so that everything should be done in a phase manner. So whatever seismic hazard we are estimating is only at the rock level, considering say site class say C site, okay, we are considering, or even B site we are considering based on the that particular area. That is called path effect. Till path effects seismic hazard study we are doing, and then site effects is done through individually, considering the particular very specific condition or location. We can go for it. So, so data collection completeness. Another is data catalog, and data like database or catalog is same. This it should be collected, and completeness is sometimes like at some cases data is missing. Suppose completeness of the is actually in some cases data is not recorded instrumentally, like before 1960 or no before no say instrument was actually there, the seismograph especially. So in that case that has been done through intensity scale, okay, intensity scale, and those destruction or the earthquake has been measured before this instrument, a seismograph or instrument. So this like data may not be recorded say properly. So in that case say data may be although earthquake has occurred, but data may not be available or may not be in recorded form. So because of that, you have to, while estimating, to extract the actual information or realistic, you want to extract the realistic information. Whatever you do, you have to take these uniform systematic data so that you can extract the correct information from that particular like source, say source or the area. Your consistent recording data are very much important here. Otherwise, your forecasting or assessment, future assessment will be giving a wrong result. Like it may not occur even what you have calculated or forecasted. So that may not occur in near future. So in that case, you have to do carefully the completeness study and find out the get out the correct information or insights of that particular seismic source. So this is one. And declustering already we have done discussed that for shocks, to remove the foreshocks and aftershocks, declustering is to be done. Even some cases when you are collecting the data from say more than one reliable sources, like USGS is one of the reliable source, another is our IMD and NGRI. So many information data website, European seismological agencies are also there. So you can take the data from anywhere, but for a single event that has occurred in on a particular area, same event actually simultaneously will be recorded in other agencies also simultaneously. So in that case, if you collect more than one agencies, so same data you may extract from other agencies also at the same time. So you may not know it. So in that case, this declustering process will help to remove those data, including foreshocks and aftershocks, actually is helping to identify the main events. So that for further studies. So that's why declustering is important here. And these are some of this is the process just shown, which is proposed by Gardner and Nopov 1974. So this is we can use it So now this is for our area, like we have considered, like for the northeast, say first what you have to do after collecting data, like earthquake data, fault information. Now after gathering all this information, you have to see how it should be delineated, like knowing the seismotectonic behavior. So based on our study which we have done here, actually we have characterized in terms of into a say four zones, major seismic source zones for the northeast, knowing the seismotectonic behaviors. These are Eastern Himalaya, Mismi region, Shillong Plateau, Myanmar Arc. So these are we have done, and these are within inside of this all these major seismic source zones. These are the fault like we have found around 20 say 13 we have found the active faults, like we have found 20 faults around. So out of that 13 faults actually are actually active, highly active. So we have considered it for our further assessment, like seismicity assessment from that understanding. And thereafter say after calculating this assessment, now next is your maximum magnitude you have to find out if for each fault. So there are several methods to find out the maximum magnitude. People have proposed in various Pigjo, like 2004 he has proposed some formulation, and Gupta 2002 he is also proposed some putting some factor 0.5 unit you have to increase or add it up with the observed magnitude. So using this you can easily find out like observed Pigjo and Gupta. So finally what we have done is for each fault this is the probable maximum magnitude we have estimated for the Assam actually. So say for all the faults up to 20 faults, putting their latitude, longitude, the fault orientations. So now this is a ground motion prediction equation that we have used for this area actually, and so this is a function of GMP, ground motion prediction equation, which is a dependent function of magnitude, distance, and other factors. But mostly magnitude and distance. Like you will see there are three equations, like we based on our data studies, the central distance and the magnitude characteristics. So there is an observed magnitude collected in various sources. We have seen we have seen that three types of equations are actually can be it can be like a permutation combination can be done to find out the realistic seismic hazard. Okay, so now for that we have like used the all the three equations, like putting a model 1, 2, 3, putting the respective equations we have developed, and we have validated, try to validate how these equations are actually mapping with respect to the observed data to ensure that our prediction will be closely accurate or agreeing with the realistic future events which will be generating the seismic hazard. So for that we have compared with the uniform hazard spectrum, or the which is a response spectrum form also for all these three models, and they are also distance period, like distance versus PGA we have compared, at least for these are for validation or the ensuring the our proposed equation is actually going to be hello. Okay শেষ হয়ে যাবে. Okay, so this is actually the just briefing part, already most of you know, and this is the response spectrum we have done for this area, and especially for typically shown here. And this is a response spectrum for this two areas typically shown. And this is for DSH and PSH what we have done using this study for all the district headquarter. Actually, we have done, and PSH also we have calculated for 2%, for 50 years, 2% for 100 years, 5%. For 50 years and 100 years, for similarly for 10%. So like that, and for the various districts we have calculated. And this is a mapping form that we have mapped for PGA values, like highest PGA values, expected values for different for all the districts. So I think so. This is also we have done for uniform hazard spectrum also, and this is also okay. This is also we have shown for like for similar study we have done for there is a Assam as Agartala, sorry, Tripura and Mizoram also we have done it. So you can go through the various our published papers. These are there. So this is for entire Northeast. We have attempted one by one to estimate this earthquake hazards at the ground, like a rock surface as well as including the site of it also. So now from the study, what we have found is actually this sagging fault, Lohit fault, and Oldham faults has maximum impact for future generating hazards among having magnitude more than 8. So and PGA values also we have seen that is varying from 0.2 to 0.31 G for 2% for 50 years, and DSH is more than 0.3 G, PGA is also. So it is say more or less it is agreeing, although here there is no answer, not considered the uncertainties, but it is giving the maximum value DSH always in most of the cases, even all cases. So that variation will be there. So okay, so I think time is not permitting. So you can go through detail if you want to know about all these studies and all. So these are given in my that profile part, so you can go through. So I think this is okay. Okay, so I think you can go through. Thank you.
Thank you, sir. Thank you for your nice presentation. And I hope that participants enjoyed. And as you have mentioned your, personal profile or email ID, so I think they can contact with their questions. So we are really sorry that we couldn't take any questions right now because our next speaker has already joined, and it's already 11:30. So thank you, sir, once again for speaking in this platform and accepting our invitation to deliver this lecture. Thank you, sir.
Thank you, Atunu, and other coordinators of this workshop. So, and thank you all the participants. Okay, thank you.
Okay, thank you, sir.
Yeah.
Okay, so on behalf of the organizing committee of DSD and SSI 2020, I welcome Professor Partha Bhattacharya, who is the speaker in this session, and I welcome all the participants also. So Professor Bhattacharya has already joined. So I think, sir, could you hear us?
Yeah, it's clear. Yeah.
Okay. So should we start, or we should check a little bit with your system and then we?
Just I open my presentation and then we can.
Yeah. So at the bottom, I think you will find that present now option at the bottom right.
Yeah, I got it actually.
Okay.
I just wanted to.
Okay.
Just a second.
So a brief introduction about Professor Partha Bhattacharya. He is presently acting as a professor in the Department of Civil Engineering of Jadavpur University. And prior to joining the Department of Civil Engineering of Jadavpur University in 2006, he worked as scientist C in National Aerospace Laboratories, Bangalore. He has received several awards from prestigious